per meter. Now, you ask me, Eugene, what is the shear flow physically? Okay, what is the shear flow physically? So now if we were to look at the cross-sectional view, so now I'm going to have my transformation now. This is my Y, this is my Z, and then using right-hand rule, rotation about X. So if our cross-sectional view look like this, right? And over here, this is our geometric centroid. And we have our, over here, this is our Vy, okay, which represent our shear force in the Y direction. So I'm going to draw our shear flow now. Okay, so our shear flow starts from here. Okay, so the length of the arrow is relative to the shear flow. Okay, i.e., the longer the length, the higher is the shear flow. Now I'm going to introduce you to a term over here. So I'm going to draw a surface now, a plane. Okay, so this plane over here, I'm drawing blue, and this plane over here, these are known as our terminals. Okay, our terminals. So the terminal, the terminus can be a plane, okay, or a point, okay, which generate or which has zero shear flow. Okay, we'll have zero shear flow. So at the top, you're going to have zero shear flow. And at the bottom, you're also going to have what? Zero shear flow. Okay, so that is the that is one thing that is very interesting. The top and the bottom are known as the terminus. We have zero shear flow. Right now, our coming back to what we are looking at. Okay, coming back to what we are looking at now. So I'm going to take this whole diagram, or I just need the 2D diagram. Okay. Now, what is interesting is this now. Okay. So you know at point A, right? If we look at an element, if I'm going to sketch an element, right? So we have determined that the element have a normal stress X, and we also have a shear XY, and then this is shear YX. Okay. Now, this element, okay, if we were to have different position of the element, so we have position I, J, K. So this is our position I, position J, and we have our position K. Okay. So if we were to have now, if we were to draw the cross-sectional area now, okay, so the cross-sectional of the beam, So we're going to have y, z, rotation about x. Okay, so I'm going to draw this cross-sectional view. Right? So I will say that this is our point over here. This is our point. I'm going to use red. This is our point I. Okay. Over here, this is our point J. Over here, this is our point K. So now, if we were to sketch our bending moment, sorry, our stresses due to bending moment. Okay, so we're going to have stresses due to bending moment. Okay, so this is our normal stress in the x direction. This is our y. Okay, so we know that over here is compression, tension. So if it's bending that way, I is in compression. Sorry, I is in tension. Okay, so our normal stress will look like this based on how the forces are acting. Okay, so at the top, we are going to be in tension. At the bottom, we are going to be in compression. Okay, so we know the magnitude over here. This is equal to stress X is equal to mz over izz multiplied by y. And for this case, you have stress X is equal to minus mz over izz multiplied by y. Okay, because the structure is, if I'm going to draw the deformation pattern looks like this, right? Right, looks like this. So this is our deformation pattern. And if we look at bending moment, okay, so we know that the moment about Z is going to be acting this way. So we have compression. And then at the top, we have tensile. Okay. Now the next thing I'm going to do is I'm going to sketch. Okay. I'm now going to sketch the diagram of the shear stress. Okay. The distribution of the shear stress. So now I'm going to sketch the distribution of the shear stress. So now over here, this is our shear stress. Okay. And then okay, this is our Y. So how the shear stress will look like? The shear stress will look like this. Later on, we're going to derive this, okay? The shear stress will have a distribution looking like this. Okay, this is the shear stress distribution, and I'm going to introduce you to the formula. That is the distribution. It will look this equation over here, right? Will be equal to 3/2 or the shear xy will be equal. Let's do the basic formula first. Okay, will be equal to Vy over Izz Qz over T, and this will in term, okay, which we will derive out, will be equal to 3/2, right? Vy over A bracket 1 minus by y squared over by c squared. Later on, we will derive this. Okay. So what's so interesting about this? Now, if I'm going to draw a line over here, right? this is known as our geometric centroid. Right? Okay, that's our, so all this line, okay, I'm going to draw a dark, thicker green. Okay, so on this axis over here, as you can see, this is where our geometric centroid is. Okay, so what's so interesting about this? Okay, why is this interesting? When we look at the bending moment, or the stresses due to the bending moment at the centroid, right? Stress X is equal to 0. Right? Now, if you look at the shear stress, shear XY max occur down here, which is in turn equal to 3/2 Vy over what? Over A. Right? So at the centroid, the normal stress is equal to 0. The shear stress is at its maximum. Okay. Well, once we are off the centroid, if you look at this point, right, we are going to have our normal stress, which is our max. However, over here, our shear XY is at the what? At the minimum, which is equal to 0. Okay. So the distribution trend, okay, across the cross-sectional area is not the same. Okay. I don't want you to worry about that yet. Later on, we were when late after shearing stress, when we watch normal stress and shearing stress together, then we worry where is the point of interest. Okay, because it is not at the centroid, right? It's not at the centroid because at the centroid, normal stress is equal to 0, shearing stress is equal to its maximum. And we also don't analyze where Y max is, means the stress X is maximum. However, your shearing stress is equal to what? The minimum. Okay, so we're going to have a bit of dilemma later on, but don't worry about that first. Okay, first let's focus on how to determine the shearing stress. Okay, the purpose of this course, okay, later on you'll see, is how we integrate 3 to 4 different topics to solve one engineering problem. Okay, that is the purpose of this course. Now, if we were to look at the shearing stress now, if we were to look at the shearing, so the shearing stress, okay, shear, the general formula, okay, looks like this. Okay, so plus minus Tx, okay, over J multiplied by R. Okay, now you guys seen this, you're like, hey, we've seen this before. And we're going to have plus minus Vy over Izz Qz divided by T. Okay. And then we're going to have plus minus Vz over Iyy. Okay. Qy over what? Over T. Okay. So this is the general formula for the shearing stress. Okay. And there's one thing that I want you to look at and compare. Okay. If now we will have a formula that is stress X, okay, this will be equal to Px over, or plus minus Px over A, plus minus, when the moment is about Y, you divide by what? Iyy multiplied by Z, plus minus, when the moment is about the Z axis, this is Izz multiplied by Y. Okay. In terms of shearing stress, when it's Vy, we use what? ZZ. In terms of bending moment, when it's My, we use what? IYY. Okay. I want you all to look at the trend. Okay. Now, based